Hello everyone, my name is Abhinav Gupta and today I'm going to present my end-term course project on Artificial Intelligence Foundations and Applications. The title of our project is Application of Artificial Intelligence in Topology Optimization of Mechanical Design and Automotive Assembly Planning. Our team comprises of two members, me and my colleague Samir, who is currently ill with COVID-19, so I'll be the one who will be presenting throughout. Now let's look at application of AI-based techniques in mechanical engineering. So the first technique is the first domain of application is topological optimization. In topological optimization, in contrast to finding the optimal design parameters for a particular structure profile, we use search-based methods to rather find an optimal structural profile based on certain design objectives. As you can see in the figure, we are not basically altering the different design parameters, we are altering the entire topology itself. In assembly planning, this is the iterative procedure aimed at finding out an optimal sequence of moves, typically of a robot, which can lead to the entire mechanical assembly of a product. As you can see in the figure, several robots could be seen assembling the cars. The application also extend to mechanism design, in which we use search-based methods to find optimal design parameters or to find a totally new set of configurations suitable for achieving a required desired motion. Examples could be origami-based designs in satellites and biorobotics. In the figure, you can see different links, gears, their combinations, and other mechanical elements like cams and shafts. Now, how these mechanisms can be assembled and what should be the appropriate link lengths in order to attain the desired motion. In this case, the desired motion is the gate pattern emulating a dog. So all these things could be done using search-based methods in AI. In our presentation, we'll be focusing more on topology optimization and assembly planning, in which we have implemented our own algorithms as well. Now let's look into the detail what is topological optimization. In topological optimization, as I already said, we try to find the optimal overall configuration of a structure rather than just finding the appropriate design parameters for a fixed design. A suitable cost function is often used and is minimized to achieve final design. One question that could come up in our mind is, why are bridges shaped like this? It could be square shaped cross-section, it could be circular cross-section, or it could be infinitely many possibilities of different cross-sections with different topologies. But it's in a particular topology, there is a good reason behind it. First, the weight is minimized, the cost is also minimized. And since we know the additional waste also means that the load is increased in individual elements, minimizing the weight indirectly also optimizes our assembly for less mechanical failure. So this is done by topological optimization. Let's look at some more applications. As I already said, optimal design of mechanical structures such as bridges, towers, and residential homes are done by topology optimization. We can minimize cost of material without compromising on reliability and mechanical failures. Aircraft design is also a different domain where topological optimization is done to minimize overall cost and improve aerodynamics and the controllability of flight. Biomechanics is another domain where topological optimization is done. We basically design processes and implants which largely rely on this method to minimize the stress shielding effects and try to imitate forces that are also applied by naturally intact bone. Now let's look at some of the existing methods. Unfortunately, in literature, nobody has used search-based methods to actually do topological optimization. The existing methods, however, include finite element methods. In the finite element methods, CAD model is built. In this case, the CAD model is of a gear. CAD model is then imported to FEM software. In this FEM software, model is meshed into large number of fine elements, and a solver calculates stresses locally using finite element methods. In step 3, nodes with very less value of stresses are iteratively removed to optimize weight cost. Now, this makes sense because if the values of stresses are low, it's very unlikely that mechanical failure will occur at that point. So why not remove that and optimize our weight cost? So final design of gear after topology optimization is this. This honeycomb structure in between and periphery is almost the same. Now, as you probably know, this is not the design of gear we are used to seeing. This is because the design, this particular honeycomb structure is very difficult to manufacture in practice. Thereby, we use this green design itself in practical. Now, evolutionary algorithms using binary coded genetic GA are also used for topological optimization in literature. These evolutionary algorithms are based on Darwin's theory of survival of the fittest. In this, we represent design configuration at any step using appropriate variables. Then we create a large number of sample solutions initially in the initial population randomly. And then we calculate fitness value of each individual solution based on the weight of the mechanical structure and the stress strain values in it. Stress strain values are important because we don't want our mechanical structure to fail ultimately. If the desired solution is reached, we stop, otherwise we continue. And when we continue, we follow these three approaches. We do selection, we do crossover, and we do mutation. Now, all these processes are basically done to create a new population. The main idea behind creating this new population is we want to retain those solutions which have higher fitness value. So we kind of bias our selection in such a manner that we consider those solutions which are giving more fitness values. Now, this is our approach when we use these search-based methods in topological optimization. So as you can see, this is a beam, this is a simply supported beam, and a load P is applied on it. And as you can see, we have divided it in different grids. So in our case, this is a 4x25 2D array. Now our task is to find the optimal design of the beam structure such that the structure is stable and the cost is minimized as well. Now, as I said, the state is defined by 2D array of 4x25 nodes such that each node xij here has value 0 or 1. If the value is 0, we are omitting that node. If the value is 1, we are considering that node in the final design. Initially, all nodes are assumed to be 1. So basically, our structure is a solid. For every intermediate state encountered by the search-based algorithms, we find out local stresses, strains at each individual node using finite element software such as ANSYS. Then we again basically import this particular model for every temporary state into the ANSYS, and we find the local stresses. Then cost is updated as C is equal to 1 by 1 plus W square, where W is defined as rho V into number of nodes. So basically W is our weight, and since we aim to minimize the weight, cost is given as inverse of 1 plus W square. The main problem here, as you probably guessed, is state space size is 2 par 4 cross 25, which is 2 par 100. It is very huge. Now let's see how we can restrict the state space to make this problem more practical. Yes, constraints. Now some of the constraints that make sense, first of all, is summation xij for every j should be greater than equal to 1, which basically means that all values inside a column can't be 0, because if that was the case, it would basically become two different structures. Same thing goes for summation xij for all I greater than equal to 1, for all j belong to 1 to 25. So these are basically all nodes in the j direction. The third constraint that we imposed is maximum deflection of every node. Maximum deflection of all nodes should be smaller than equal to a threshold value. This is done because we want some level of structural rigidity in our design. The fourth and last constraint is that our system shouldn't fail. The condition to prevent that is the von Mises yield stress criteria. And this is represented as follows. Maximum von Mises stress at any node should be smaller than the maximum allowable von Mises stress at any node to prevent mechanical failure. We have considered factor of safety to be 2 in our design. Now, even after applying these many constraints, our search space is still huge. We want to further minimize our search space so that our algorithm converges faster. So what we came up with is the iterative state space pruning. After every k iterations of our algorithm, the nodes with very small stress values, where the chances of failure are very less, are automatically pruned and removed from our state space. For our purposes, the value of k iterations is 25 iterations, and the value of stress, where the pruning will occur, is equal to sigma yield by 4. So basically, sigma yield is the stress where the structure will mechanically fail. And if the values of stresses at any node is 1/4 of that value, we'll simply remove that node because that node is not required for optimal design. Now, when we ran this algorithm, we got the final results. As you can see, the resolution is very, very poor because first of all, like we took very less number of nodes, only 100 nodes, while the state-of-the-art finite element software takes lakhs of nodes. But initial stages, we took only 100 nodes. The ideal result should have been this. Our results reasonably represent the ideal result, but it's nowhere close. Our present challenges include finite element software such as ANSYS are very computationally heavy. And since our present approach involves calculation of local stresses at any node using ANSYS software, our entire code runs a little bit slow. We can make some efforts to minimize this dependency on ANSYS by using theoretical differential equations arising from Euler-Beam elastic theory. Even after so many constraints, the state space is definitely pretty massive, and a lot of assumptions have been made to achieve the solution, which is significantly poor in comparison to those reported in literature. Efforts should also be made to accommodate large number of nodes without compromising easy computation. And one of the reasons we couldn't implement topological optimization on large number of nodes in a small time frame is the lack of heuristics in our modeling method. So maybe in future we should consider using heuristics so we can further prune the state space and explore the different nodes intelligently. Existing trust designs could come handy as a good heuristic in future. Now, this is another domain which we explored and read a lot of literature, which is car assembly automation using artificial intelligence and robotics. Now, assembly automation comes in between the process of design and process of manufacturing. And this entire process of assembly automation is further divided into disassembly path planning, assembly design, and sequence optimization. Now, let's look at the first, disassembly path planning. In this process, we basically model the rigid body to be disassembled and the environment in configuration space. Multi-robot planning approaches can be adopted where several rigid bodies should reach goal state from a start space without colliding. So basically, if we have assembly, it's basically accumulation of a large number of parts, right? Organized in a single manner so that they can build up the entire product, our entire assembly. Now, when we do disassembly path planning, our goal is to find the optimal planning algorithm such that this assembly could be disassembled into individual parts. In order to do that, in literature, A-star algorithm has been used. And as you can see in the figure, this is the benchmark problem of pentomony puzzle. And an algorithm was proposed by authors in these papers using A-star, and the final planning algorithm, when applied, could disassemble the pentomony puzzle into its individual parts. The another process is assembly design. In the assembly design, it involves modeling mating features and locating schemes such that the final product has desired quality robustness. So basically, the way in which we do assembly can alter the desired quality of our entire assembly, because different manufacturing methods can yield different quality results. DAGs, which are directed acyclic graphs, are often used in literature, and a directed edge from node A to node B represents that part A locates part B, as you can see in the figure. Now, this can be partial or total. Designer uses tools to perform tolerance analysis. Tolerance is again the criteria of assuring quality, to choose appropriate locating schemes. Now, as you can see in the figure, in this figure, A is directly connected to B to directly connected to C. Now, this is the weak form of connection because it locates B and C partially, not completely in Cartesian space. While in the second figure, they are strongly connected. So A locates both B and C completely. Now comes the third process, sequence optimization, and we shall focus our main. We should focus more on this sequence optimization in following slides as well. So it involves finding a sequence of operations that assemble the final product while optimizing some cost measure. Sequences can be represented using license-based approach. So there is a license-based graph, which we can discuss in the future slides, and the state space approach as well. This process of sequence optimization using the modules of assembly design as well as the disassembly path planning in it as well. As you can see in the figure, if we are to apply this particular locating scheme as given in this strongly connected figure, we cannot possibly make assembly of this type, because for making the assembly of this type, we should first make a subassembly BC, and then we should place subassembly BC inside the part A. Otherwise, it can never be assembled. So these parts cannot be assembled linearly. Now, this is some of the methods which have been discussed in literature for sequence optimization. So these are the methods of representation. First is license graphs based approach. Now, before we go on to these approaches, let's first look at the predefined locating scheme. So this locating scheme has to be given us by the designer itself, based on the geometric quality and the tolerance which have to be which is desired in the final product. So this is basically the desired locating schemes. A locates B, A locates C, A locates C, and then C locates D and E, right? But even in this desired locating schemes, there could be many paths that could lead us to the final product. And we used different approaches to model those paths. One of those approaches is Lyson graphs based approach. So initially, all these blocks EAB, which basically represents the edge cost AB, edge cost ACE subassembly, edge cost of AC subassembly, and edge cost of CD subassembly, all these are empty in the initial state. Our final goal is to reach this state where we have assembled the final product. As you can see, there are multiple paths. We could go this way, we could go this way, we could go this way. And there are multiple paths. So this is basically a OR graph, which represents the implicit state space from initial configuration to the final configuration. Mind you, we have omitted some possible configurations while making this Lyson graphs as well, because those configurations and state transformation are restricted by the very fact that the designer has given this very specific locating scheme that restricts our state space. Same goes for the another approach, parts state space approach, in which we do it in a reverse process. We consider first the final assemblies A, B, C, D, E, and then we keep on disassembling this. So it could go A, B, C, D, A, B, C, E, A, B, C, D, E. There are other ways it could go into other possible configurations as well. But like I said, this locating schemes restrict all those methods. Otherwise, we could reach Bell numbers in this state space. So Bell numbers are basically the total number of partitions which we can make of any configuration. And they expand exponentially. So the number of ways of partitioning a assembly of A, B, C, D, E could be A plus B plus C plus D plus E, could be A plus B plus C, D, E, could be A, B, C plus D plus E. So there are like many number of ways, but all those ways are restricted by the fact that designer has already provided us a locating scheme. Now, once we have these Lyson graphs or part state space, what we can do is we can give them some cost functions, right? So one of the cost function we could be interested in giving them time, assigning each step an individual time based on the complexity of the task, right? It could be done by considering the amount of rotations and translations of the parts needed. So if the amount of rotation and translation of part needed in assembling an individual product or disassembling it is very huge, then maybe the time consumed by it is very large. We can also consider the length of the disassembling path as a cost function as well, and we can aim to minimize it. Now, since the Lyson graph is a OR graph and this part state space is a compositional graph, so for optimizing this entire assembly in Lyson graph-based approach, we use A-star algorithm, which works for OR graphs. And for part state space approach, we use AO-star algorithm, which works on compositional graphs. Now let's look at our implementation of how we implemented this entire sequencing process. We didn't do the initial disassembly path planning and assembly design because we had less time, but we did sequence optimization. So let's look at how we implemented sequence planning. So initially, we have the information on the states, actions, preconditions, and their actions, their preconditions and effects. And we give this information to a high-level planner, and we use PTDL language for this purpose. The output of this high-level planner is a certain sequence of tasks, which we further feed to low-level planner, which we have built in MATLAB. So what this low-level planner does is that it gives us required joint angle trajectory commands for our robot. So these are the actions which we have designed. One of the actions is, I haven't included all of the actions because they were very huge. So one of the action is attached to chassis, in which we basically attach this particular part to the chassis of the car. It has some preconditions. If the part is still not attached to the assembly, first, if the configuration is appropriate for attaching, It has some effects that part is attached to the chassis finally. Part is not free now. Configuration is updated. Second action is attach, where we give two parameters, part 1 and part 2. Precondition requires that part 1 is still not attached to the assembly. If the configuration is appropriate for attaching, that is also a precondition. And if the part 2 is free, so that part 1 can be easily attached. Now, effect is part 1 is attached to part 2 in the assembly. Configuration is then updated. Part 1 is not free is also the effect, and part 2 is not free to attach any part on it. These are the effects. Now, these are our fluents. We have considered several objects such as engine, hood, suspension, tire pair 1, tire pair 2, all of these while designing the car assembly. Although this is much less complex to the practical system. Now, our planning algorithm's goal is to put initial state to a final goal state following all these constraints. So these are the results we got when we built our code in PDDL. As you can see, so the total computational time is 0.068 seconds, and nodes expended are 90, and nodes generated during search on 1896. This is the final plan. These are the different tasks which have to be done sequentially in order to do the complete assembly.